Oofs! Look at the car, it's completely rusted. It was a great shot, dude. Cutting wood and melting ice are examples of physical changes. On the other hand, the rusting of iron, burning of wood, and eggs cooked into an omelette are examples of chemical changes. Hey! I will show you something. This is a physical change. Let me burn this. I need some charcoal. Now this is a chemical change.
There are two types of changes, physical and chemical. Physical changes are temporary, and chemical changes are permanent. Substances can undergo either physical or chemical changes to form new substances. In this lesson, you will learn about elements, mixtures, and compounds. At the end of this lesson, you will be able to define physical and chemical changes, identify the types of change, given an example, define pure substances and mixtures, list the properties of elements, mixtures, and compounds, and categorize substances into elements, mixtures, and compounds. Have you ever observed an ice cube kept outside the refrigerator for some time?
Ice melts and changes to water.
Yes, there is a change in the state of the ice cube. Now, let's do a small experiment. For this, we need to take 2 beakers with 20 grams of sugar and label them as A and B. Let's add some water to beaker A and stir it. In beaker B, we will add a little sulfuric acid. Now, observe what happens in beaker A. The sugar gets dissolved in water. In beaker B, sugar reacts with sulfuric acid and black sugar charcoal is formed. From this, we can say that the change that has taken place in beaker A is a physical change, whereas the change that has taken place in beaker B is a chemical change. In beaker A, we can get back the sugar by the evaporation of water. On the other hand, in beaker B, we cannot get back the sugar from the carbon. From this observation, we can conclude that there are two types of changes: physical change and chemical change.
How do we define a physical and a chemical change?
After observing the experiment, we can define a physical change as a temporary change in which the composition of the substance remains same and no new substance is formed, but only a change of state occurs. Melting of ice, breaking of glass, tearing of paper, cutting of wood, and changing of water to water vapor are examples of physical change. Likewise, we can define a chemical change as a permanent change in which a new substance is formed that has properties which are different from the original substance. For example, formation of water from hydrogen and oxygen atoms, rusting of iron, burning of wood, lighting of firecrackers, burning of a matchstick. You might have observed the word pure written on the packing of consumables like milk, mineral water, fruit juice, etc. What does the word pure mean to you?
It means having no adulteration.
That's right, but for a chemist, none of these substances are pure. For example, milk is a mixture of water, fat, and proteins. Mineral water, according to the label, has calcium chloride, magnesium sulfate, and sodium sulfate. If it were really pure water, In the scientific meaning of the word, it should contain only water molecules. For a chemist, the purity of a substance means the substance is made up of only one type of a particle. The particles may be atoms or molecules. For example, the element iron is made of only one kind of a particle called iron atoms. So iron is a pure substance. From this, we can define a pure substance as a substance which is made of only one kind of a particle. For example, iron, aluminium, silver, and gold.
Okay. So, the substances that are opposite to pure are mixtures?
For a chemist, when a substance contains more than one type of a particle, it is known as a mixture. For example, salt solution is made up of two components, salt and water. Therefore, salt solution is a mixture.
There are over 100 known elements on Earth.
A pure substance which is made up of only one kind of atom and cannot be broken into two or more simpler substances by physical or chemical means is referred to as an element. For example, iron, gold, and silver.
How does one identify the elements? Do they have any typical properties?
Yes, they do have typical properties. Let's look at some of the characteristics of elements. An element is homogeneous in nature. It is a pure substance, made up of only one kind of atom. For example, iron and silver are made of only iron and silver atoms. An element cannot be broken down into simpler substances by any physical or chemical methods, such as heat, light, electricity, or chemical reactions with other substances. For example, if you want to smash a piece of iron into small pieces or heat it, the piece still remains as the element iron. An atom is the smallest unit that shows all the properties of an element. For example, an atom of iron shows all the properties of that metal. Elements have sharp melting and boiling points. For example, aluminium has a boiling point of 2447 degrees centigrade. Elements can be classified into three classes: metals, non-metals, and metalloids.
Hey! Chocolates!
Did you observe they were wrapped in aluminium foil? Not only chocolates, but biscuits and medicines are wrapped in aluminium foil. This aluminium is a metal. Over 80% of known elements are metals. Let's see what metals are and their properties. Metals are the elements which readily lose electrons to form positive ions or cations. For example, sodium, an alkali metal, loses an electron and forms positively charged sodium ion. Let's observe some of the properties of metals. Metals have luster. When freshly cut, they show metallic luster. For example, gold. Metals are good conductors of heat and electricity. As metals have free electrons in them, they are able to conduct heat and electricity. For example, copper. Metals are malleable, meaning they can be hammered into thin sheets. For example, aluminium. Metals are ductile, which means they can be drawn into wires. For example, copper. Metals are sonorous. They give a ringing sound when they are hit by a hard iron rod. For example, copper. Almost all metals are solids except mercury, which is a liquid at room temperature.
Is sodium chloride a metal?
No, it's not. Let me tell you about nonmetals. They are the elements which readily gain electrons to form negative ions or anions. For example, chlorine accepts electrons from a metal like sodium and forms a negatively charged chloride anion.
Like metals, do nonmetals also have properties?
Yes, of course. Let's look at some of the properties of nonmetals. Nonmetals usually show some or all of the following properties. They do not exhibit luster. Nonmetals are bad conductors of heat and electricity. They do not contain free electrons in them, so they do not conduct heat and electricity. For example, sulfur. They are not malleable. They cannot be drawn into sheets. For example, sulfur and phosphorus. Nonmetals are non-ductile. They cannot be drawn into wires. For example, phosphorus. They are not sonorous. When hit by any hard substance, they do not produce any sound. For example, carbon. Nonmetals exist in all the three states. Thus, 11 nonmetals are gases. Only bromine is a liquid, and the others are solids. The elements which have intermediate properties between those of metals and nonmetals are called metalloids. They are amphoteric in nature. Metalloids react both with acids and bases. For example, boron, silicon, and germanium.
Are water and carbon dioxide gases, not mixtures?
No.
Why? If we take the example of water, it is made up of two kinds of atoms.
Yes, you are right. Water is made up of oxygen and hydrogen atoms, but still, it is a pure substance.
How?
Water and carbon dioxide are examples of compounds.
Compounds? Another set of substances.
No, not quite. A compound is a pure substance that is composed of two or more elements, chemically combined in definite proportion by weight. For example, water is made up of 2 atoms of hydrogen and 1 atom of oxygen. These atoms combine to form a compound known as water. The smallest particle of water is called a molecule. A molecule is the smallest particle of a compound that still has all the properties of a compound. Water, ammonia, carbon dioxide, and limestone are examples of compounds.
Is salt solution a compound?
No, it is not. Even compounds have similar properties like that of elements. Compounds are composed of 2 or more elements which are chemically bound with one another in fixed proportions. Let's look at some of the characteristics of compounds. A pure chemical compound is homogeneous in nature, made up of the same type of molecules. For example, water contains only molecules of water. A compound can be broken into its constituents. For example, water can be broken into constituent elements, hydrogen and oxygen, by the process of electrolysis. A compound has a fixed composition. For example, a water molecule is always composed of 2 hydrogen atoms and 1 oxygen atom. A compound has a distinct set of properties which is not similar with the properties of its constituent elements. For example, sodium chloride, table salt, is a harmless substance which is a white crystalline solid. On the other hand, its constituents, sodium, is a greyish-white solid, and chlorine is a greenish-yellow gas that are potentially dangerous. Sodium is a highly reactive metal which catches fire when exposed to air, and chlorine is highly poisonous. From this we can say that compounds exhibit a distinct set of properties. A compound has a sharp melting and boiling point. For example, water has a boiling point of 100 degrees centigrade and a melting point of 0 degrees centigrade.
Hey, what about vegetable salad? I like it. It's so colorful. Is it a mixture?
Yes, you're right. Observe carefully. The salad contains a variety of vegetables like carrot, cucumber, beetroot, tomato, cabbage, and onion. You can segregate each of the vegetables from one another, isn't it?
Yes. So, vegetable salad is a mixture.
A mixture is matter that consists of two or more substances which may be elements, compounds, or both mixed together physically in any proportion, but not chemically combined. For example, air is a mixture of gases like oxygen, nitrogen, carbon dioxide, etc. These gases are not chemically combined with one another and can be separated by suitable means. Based on the distribution of the particles in the mixture, there are two types of mixtures, heterogeneous and homogeneous mixture. A mixture that is not uniform throughout is called a heterogeneous mixture. For example, a mixture of sugar and salt is a heterogeneous mixture because the sugar and salt particles can be segregated based on their color and size. Examples of heterogeneous mixtures are iron fillings and sulfur powder, concrete, which is a mixture of cement, water, sand, etc. The second type of mixture is a homogeneous mixture. Observe the solution. This is a solution of salt in water. How does this salt solution appear to you? It looks uniform throughout. So, such a type of mixture is known as a homogeneous mixture. Brass, a mixture of copper and zinc. Salt solution, a mixture of salt in water, and a solution of alcohol in water are examples of homogeneous mixtures. Now, let's observe some of the properties of a mixture. There is no definite proportion in which the constituents of a mixture combine. For example, the mixture of salt and sand can be in any ratio. The parts of a mixture can be separated by physical means. For example, a mixture of iron filings and sulfur can be separated by using a magnet. When a magnet is placed in the above mixture of iron filings and sulfur, the iron particles are attracted by the magnet, while sulfur particles remain unattracted. When a mixture is created, no new substance is formed. Each part of a mixture retains its own properties. For example, we could mix various proportions of hydrogen and oxygen gas. As long as you do not ignite the mixture, the combination will form a mixture that can be separated. Energy is neither given out nor absorbed in the preparation of a mixture. For example, no heat or light energy is liberated or absorbed when iron filings and sulfur are mixed together. A mixture does not have a sharp melting or boiling point. For example, sugar solution does not boil at a fixed temperature.